The following is a conversation with Sean Carroll, part 2, the second time we've spoken on the podcast. You can get the link to the first time in the description. This time we focus on quantum mechanics and the many worlds interpretation that he details elegantly in his new book titled Something Deeply Hidden. I own and enjoy both the ebook and audiobook versions of it. Listening to Sean read about entanglement, complementarity, and the emergence of spacetime reminds me of Bob Ross teaching the world how to paint on his old television show. If you don't know who Bob Ross is, you're truly missing out. Look him up. He'll make you fall in love with painting. Sean Carroll is the Bob Ross of theoretical physics. He's the author of several popular books, a host of a great podcast called Mindscape, and is a theoretical physicist at Caltech and the Santa Fe Institute, specializing in quantum mechanics, arrow of time, cosmology, and gravitation. This is the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, give it 5 stars on iTunes, support it on Patreon, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D-M-A-N. And now, here's my conversation with Sean Carroll. Isaac Newton developed what we now call classical mechanics that you describe very nicely in your new book, as you do with a lot of basic concepts in physics. So what's classical mechanics? I can throw a rock and can predict the trajectory of that rock's flight. But if we could put ourselves back into Newton's time, his theories work to predict things, but as I understand, he himself thought that their interpretations of those predictions were absurd. Perhaps he just said it for religious reasons and so on. But in particular, sort of a world of interaction without contact. So action at a distance. It didn't make sense to him on a sort of a human interpretation level. Does it make sense to you that things can affect other things at a distance?
It does, but, that was one of Newton's worries. You're actually right in a slightly different way about the religious worries. He was smart enough, this is off the topic, but still fascinating. Newton almost invented chaos theory as soon as he invented classical mechanics. He realized that in the solar system, so he was able to explain how planets move around the sun, but typically you would describe the orbit of the Earth, ignoring the effects of Jupiter and Saturn and so forth, just doing the Earth and the Sun. He kind of knew, even though he couldn't do the math, that if you included the effects of Jupiter and Saturn and the other planets, the solar system would be unstable, like the orbits of the planets would get out of whack. So he thought that God would intervene occasionally to sort of move the planets back into orbit, which is only way you could explain how they were there, presumably forever. But the worries about classical mechanics were a little bit different. The worry about gravity in particular. It wasn't a worry about classical mechanics. It was a worry about gravity. How in the world does the Earth know that there's something called the sun 93 million miles away that is exerting a gravitational force on it? And he literally said, I leave that for future generations to think about because I don't know what the answer is. And in fact, people underemphasize this, but future generations figured it out. Pierre-Simon Laplace in circa 1800 showed that you could rewrite Newtonian gravity as a field theory. So instead of just talking about the force due to gravity, you can talk about the gravitational field or the gravitational potential field. And then there's no action at a distance. It's exactly the same theory empirically. It makes exactly the same predictions. But what's happening is instead of the sun just reaching out across the void, there is a gravitational field in between the sun and the Earth that obeys an equation, Laplace's equation, cleverly enough, and that tells us exactly what the field does. So even in Newtonian gravity, you don't need action at a distance. Now, what many people say is that Einstein solved this problem because he invented general relativity. And in general relativity, there's certainly a field in between the Earth and the sun, but also there's the speed of light as a limit. In Laplace's theory, which was exactly Newton's theory, just in a different mathematical language, there could still be instantaneous action across the universe. Whereas in general relativity, if you shake something here, its gravitational impulse radiates out at the speed of light, and we call that a gravitational wave, and we can detect those. So, but I really it rubs me the wrong way to think that we should presume the answer should look one way or the other. Like if it turned out that there was action at a distance in physics and that was the best way to describe things, then I would do it that way. It's actually a very deep question, because when we don't know what the right laws of physics are, when we're guessing at them, when we're hypothesizing at what they might be, we are often guided by our intuitions about what they should be. I mean, Einstein famously was very guided by his intuitions, and he did not like the idea of action at a distance. We don't know whether he was right or not. It depends on your interpretation of quantum mechanics, and it depends on even how you talk about quantum mechanics within any one interpretation.
So if you see every force as a field or any other interpretation of action at a distance, I mean, it's just stepping back to sort of caveman thinking. Like, can you really sort of understand what it means for a force to be a field that's everywhere? So if you look at gravity, like what do you think about?
I think so.
So is this something that you've been conditioned by society to think that, to map the fact that science is extremely well predictive of something to believing that you actually understand it, like you can intuitively to the degree that human beings can understand anything, that you actually understand it? Or are you just trusting the beauty and the power of the predictive power of science?
That depends on what you mean by this idea of truly understanding something, right? You know, I mean, can I truly understand Fermat's last theorem? You know, it's easy to state it, but do I really appreciate what it means for incredibly large numbers, right? Yeah, I think I do understand it. But like, if you want to just push people on, well, but your intuition doesn't go to the places where Andrew Wiles needed to go to prove Fermat's last theorem, then I can say, fine, but I still think I understand the theorem. And likewise, I think that I do have a pretty good intuitive understanding of fields pervading space-time, whether it's the gravitational field or the electromagnetic field or whatever, the Higgs field. Of course, one's intuition gets worse and worse as you get trickier in quantum field theory and all sorts of new phenomena that come up in quantum field theory. So our intuitions aren't perfect. But I think it's also okay to say that our intuitions get trained, right? Like, you know, I have different intuitions now than I had when I was a baby. That's okay. That's not, an intuition is not necessarily intrinsic to who we are. We can train it a little bit.
So that's where I'm going to bring in Noam Chomsky for a second, who thinks that our cognitive abilities are sort of evolved through time. And so they're biologically constrained. And so there's a clear limit, as he puts it, to our cognitive abilities. And it's a very harsh limit. But you actually kind of said something interesting, the nature versus nurture thing here, is we can train our intuitions to sort of build up the cognitive muscles to be able to understand some of these tricky concepts. So do you think there's limits to our understanding that's deeply rooted, hard-coded into our biology that we can't overcome?
There could be limits to things like our ability to visualize, okay? But when someone like Ed Witten proves a theorem about, 100-dimensional mathematical spaces, he's not visualizing it, he's doing the math. That doesn't stop him from understanding the result. I think, and I would love to understand this better, but my rough feeling, which is not very educated, is that, there's some threshold that one crosses in abstraction when one becomes kind of like a Turing machine, right? One has the ability to contain in one's brain logical, formal, symbolic structures and manipulate them. And that's a leap that we can make as human beings that dogs and cats haven't made. And once you get there, I'm not sure that there are any limits to our ability to understand the scientific world at all. Maybe there are. There's certainly limits on our ability to calculate things, right? People are not very good at taking cube roots of million-digit numbers in their head. But that's not a limit of understanding. It's certainly not a limit in principle.
So, of course, as a human, you would say there doesn't feel to be limits to our understanding. But sort of, have you thought that the universe is actually a lot simpler than it appears to us, and we just will never be able to, like, it's outside of our, okay, so our cognitive abilities combined with our mathematical prowess and whatever kind of experimental simulation devices we can put together. Is there limits to that? Is it possible there's limits to that?
Well, of course it's possible that there are limits to that. Is there any good reason to think that we're anywhere close to the limits is a harder question. Look, imagine asking this question 500 years ago to the world's greatest thinkers, right? Like, are we approaching the limits of our ability to understand the natural world? And by definition, there are questions about the natural world that are most interesting to us that are the ones we don't quite yet understand, right? So we're always faced with these puzzles we don't yet know. And I don't know what they would have said 500 years ago, but they didn't even know about classical mechanics, much less quantum mechanics. So we know that they were nowhere close to how well they could do, right? They could do enormously better than they were doing at the time. I see no reason why the same thing isn't true for us today. So of all the worries that keep me awake at night, the human mind's inability to rationally comprehend the world is low on the list.
Well put. So one interesting philosophical point that quantum mechanics bring up is that you talk about the distinction between the world as it is and the world as we observe it. Mm-hmm. So staying at the human level for a second, how big is the gap between what our perception system allows us to see and the world as it is outside our mind's eye, sort of not at the quantum mechanical level, but as just these particular tools we have, which is the few senses and cognitive abilities to process those senses?
Well, that last phrase, having the cognitive abilities to process them, carries a lot, right? I mean, there is our sort of intuitive understanding of the world. You don't need to teach people about gravity for them to know that apples fall from trees, right? That's something that we figure out pretty quickly. Object permanence, things like that. The three-dimensionality of space, even if we don't have the mathematical language to say that, we kind of know that it's true. On the other hand, no one opens their eyes and sees atoms. Right? Or molecules, or cells for that matter. Forget about quantum mechanics. So, but we got there. We got to understanding that there are atoms and cells using the combination of our senses and our cognitive capacities. So adding the ability of our cognitive capacities to our senses is adding an enormous amount. And I don't think there's a hard and fast boundary. You know, if you believe in cells, if you believe that we understand those, then there's no reason you believe we can't believe in quantum mechanics just as well.
What to you is the most beautiful idea in physics?
Conservation of momentum.
Can you elaborate?
Yeah. If you were Aristotle, when Aristotle wrote his book on physics, he made the following very obvious point. We're on video here, right? So people can see this. Yes. So if I push the bottle, let me cover this bottle so we do not have a mess. But okay, so I push the bottle, it moves. And if I stop pushing, it stops moving. Yes. And this kind of thing is repeated a large number of times all over the place. If you don't keep pushing things, they stop moving. This is a indisputably true fact about our everyday environment, okay? And for Aristotle, this blew up into a whole picture of the world in which things had natures and teleologies, and they had places they wanted to be. And when you were pushing them, you were moving them away from where they wanted to be, and they would return and stuff like that. And it took 1,000 years or 1,500 years for people to say, actually, if it weren't for things like dissipation and air resistance and friction and so forth, the natural thing is for things to move forever in a straight line at the constant velocity, right? Conservation of momentum. And that is the reason why I think that's the most beautiful idea in physics, is because it shifts us from a view of natures and teleology to a view of patterns in the world. So when you were Aristotle, you needed to talk a vocabulary of why is this happening? What's the purpose of it? What's the cause, et cetera? Because, its nature does or does not want to do that. Whereas once you believe in conservation momentum, things just happen. They just follow the pattern. You have Laplace's demon, ultimately, right? You give me the state of the world today. I can predict what it's going to do in the future. I can predict where it was in the past. It's impersonal, and it's also instantaneous. It's not directed toward any future goals. It's just doing what it does given the current state of the universe. That I think even more than either classical mechanics or quantum mechanics, that is the profound, deep insight that gets modern science off the ground. You don't need natures and purposes and goals. You just need some patterns.
So it's the first moment in our understanding of the way the universe works where you branch from the intuitive physical space to kind of the space of ideas. And also the other point you said, which is conveniently, most of the interesting ideas are acting in the moment. You don't need to know the history of time or the future.
And of course, this took a long time to get there, right? I mean, the conservation of momentum itself took hundreds of years. It's weird because like someone would say something interesting and then the next interesting thing would be said like 150 or 200 years later, right? They weren't even talking to each other. They were just reading each other's books. And probably the first person to directly say that in outer space, in the vacuum, a projectile would move at a constant velocity was Avicenna, Ibn Sina in the Persian Golden Age, circa 1000. And he didn't like the idea. He used that, just like Schrodinger used Schrodinger's cat to say, surely you don't believe that, right? Mm-hmm. Ibn Sina was saying, surely you don't believe there really is a vacuum, because if there was a really vacuum, things could keep moving forever, right? But still, he got right the idea that there was this conservation of something, impetus or mile, he would call it. And that's 500 years, 600 years before classical mechanics and Isaac Newton. So, Galileo played a big role in this, but he didn't exactly get it right. And so it just takes a long time for this to sink in because it is so against our everyday experience.
Do you think it was a big leap, a brave or a difficult leap of sort of math and science to be able to say that momentum is conserved?
I do. I think it's a example of human reason in action. Even Aristotle knew that his theory had issues because you could fire an arrow and it would go a long way before it stopped. So if his theory was things just automatically stop, what's going on? And he had this elaborate story. I don't know if you've heard the story, but the arrow would push the air in front of it away, and the molecules of air would run around to the back of the arrow and push it again. And like anyone reading this is going like, really? That's what you thought? But it was that kind of thought experiment that ultimately got people to say, like, actually, no, if it weren't for the air molecules at all, the arrow would just go on by itself. And it's always this give and take between thought and experience, back and forth, right? Theory and experiment, we would say today.
Another big question that I think comes up certainly with quantum mechanics is, what's the difference between math and physics to you?
To me, very, very roughly, math is about the logical structure of all possible worlds, and physics is about our actual world.
And it just feels like our actual world is a gray area when you start talking about interpretations of quantum mechanics, or no?
I'm certainly using the word world in the broadest sense, all of reality. So I think that reality is specific. I don't think that there's every possible thing going on in reality. I think that there are rules, whether it's the Schrodinger equation or whatever. So I think that there's a sensible notion of the set of all possible worlds, and we live in one of them. The world that we're talking about might be a multiverse, might be many worlds of quantum mechanics, might be much bigger than the world of our everyday experience, but it's still one physically contiguous world in some sense.
But so if you look at the overlap of math and physics, it feels like when physics tries to reach for understanding of our world, it uses the tools of math to sort of reach beyond the limit of our current understanding. What do you make of that process of sort of using math to, so you start maybe with intuition, or you might start with the math and then build up an intuition, but this kind of reaching into the darkness, into the mystery of the world with math?
Well, I think I would put it a little bit differently. I think we have theories of the physical world, which we then extrapolate and ask, what do we conclude if we take these seriously well beyond where we've actually tested them? It is separately true that math is really, really useful when we construct physical theories. And, famously, Eugene Wigner asked about the unreasonable success of mathematics and physics. I think that's a little bit wrong, because anything that could happen, any other theory of physics that wasn't the real world but some other world, you could always describe it mathematically. It's just that it might be a mess. The surprising thing is not that math works, but that the math is so simple and easy that you can write it down on a t-shirt, right? I mean, that's what is amazing. That's an enormous compression of information that seems to be valid in the real world. So that's an interesting fact about our world, which maybe we could hope to explain or just take as a brute fact. I don't know. But once you have that, there's the indelible relationship between math and physics. But philosophically, I do want to separate them. What we extrapolate, we don't extrapolate math because there's a whole bunch of wrong math, that doesn't apply to our world, right? We extrapolate the physical theory that we best think explains our world.
Again, an unanswerable question. Why do you think our world is so easily compressible into beautiful equations?
Yeah, I mean, like I just hinted at, I don't know if there's an answer to that question. There could be.
What would an answer look like?
Well, an answer could look like if you showed that there was something about our world that maximized something, the mean of the simplicity and the powerfulness of the laws of physics, or whether maybe we're just generic. Maybe in a set of all possible worlds, this is what the world would look like, right? Like I don't really know. I tend to think not. I tend to think that there is something specific and rock bottom about the facts of our world that don't have further explanation, like the fact that the world exists at all, and furthermore, the specific laws of physics that we have. I think that in some sense, we're just going to, at some level, we're going to say, and that's how it is. And, we can't explain anything more. I don't know if we're anywhere close to that right now, but that seems plausible to me.
And speaking of rock bottom, one of the things sort of your book kind of reminded me or revealed to me is that what's fundamental and what's emergent, it just feels like I don't even know anymore what's fundamental in physics, if there's anything. It feels like everything, especially with quantum mechanics, is revealing to us is that most interesting things that I would, as a limited human, would think are fundamental can actually be explained as emergent from the more deeper laws.
I mean, we don't know, of course. We had to get that on the table. We don't know what is fundamental. We do have reason to say that certain things are more fundamental than others, right? Mm-hmm. Atoms and molecules are more fundamental than cells and organs. Quantum fields are more fundamental than atoms and molecules. We don't know if that ever bottoms out. I do think that there's sensible ways to think about this. If you describe something like this table as a table, it has a height and a width, and it's made of a certain material, and it has a certain solidity and weight and so forth. That's a very useful description as far as it goes. There's a whole nother description of this table in terms of a whole collection of atoms strung together in certain ways. The language of the atoms is more comprehensive than the language of the table. You could break apart the table, smash it to pieces, still talk about it as atoms, but you could no longer talk about it as a table, right? So I think that this comprehensiveness, the domain of validity of a theory, gets broader and broader as the theory gets more and more fundamental.
So what do you think Newton would say, maybe write in a book review, if you read your latest book on quantum mechanics, Something Deeply Hidden?
It would take a long time for him to think that any of this was making any sense.
You catch him up pretty quick in the beginning.
Yeah.
you give him a shout out in the beginning.
That's right. I mean, he was the man. I'm happy to say that Newton was the greatest scientist who ever lived. I mean, he invented calculus in his spare time, which would have made him the greatest mathematician just all by himself, right? All by that one thing. But of course, it's funny because Newton was in some sense still a pre-modern thinker. Rocky Kolb, who was a cosmologist at the University of Chicago, said that, Galileo, even though he came before Newton, was a more modern thinker than Newton was. Like if you got Galileo and brought him to the present day, it'd take him 6 months to catch up, and then he'd be in your office telling you why your most recent paper was wrong. Whereas Newton just thought in this kind of more mystical way. He wrote a lot more about the Bible and alchemy than he ever did about physics. And but he was also more brilliant than anybody else and way more mathematically astute than Galileo. So I really don't know. He might just say like, give me the textbooks, leave me alone for a few months, and then be caught up. But he might have had mental blocks against seeing the world in this way. I really don't know.
Or perhaps find an interesting mystical interpretation of quantum mechanics.
Very possible, yeah.
Is there any other scientists or philosophers through history that you would like to know their opinion of your book?
That's a good question. I mean, Einstein is the obvious one, right? He was not that long ago, but I even speculate at the end of my book about what his opinion would be. Yeah. I am curious as to, what about older philosophers like Hume or Kant, right? Like, what would they have thought, or Aristotle, what would they have thought about modern physics? Because they do, in philosophy, your predilections end up playing a much bigger role in your ultimate conclusions because you're not as tied down by what the data is. In physics, physics is lucky because we can't stray too far off the reservation as long as we're trying to explain the world that we actually see in our telescopes and microscopes. But it's just not fair to play that game because the people we're thinking about didn't know a whole bunch of things that we know, right? Like we lived through a lot that they didn't live through. So by the time we got them caught up, they'd be different people.
So let me ask a bunch of basic questions. I think it'll be interesting, useful for people who are not familiar, but even for people who are extremely well familiar. Let's start with, what is quantum mechanics?
Quantum mechanics is the paradigm of physics that came into being in the early part of the 20th century that replaced classical mechanics. And it replaced classical mechanics in a weird way that we're still coming to terms with. So in classical mechanics, you have an object, it has a location, has a velocity, and if you know the location and velocity of everything in the world, you can say what everything's going to do. Quantum mechanics has an aspect of it that is kind of on the same lines. There's something called the quantum state or the wave function. And there's an equation governing what the quantum state does. So it's very much like classical mechanics. The wave function is different. It's sort of a wave. It's a vector in a huge dimensional vector space rather than a position and a velocity. But okay, that's a detail. And the equation is the Schrödinger equation, not Newton's laws, but okay, again, a detail. Where quantum mechanics really becomes weird and different is that there's a whole nother set of rules in our textbook formulation of quantum mechanics, in addition to saying that there's a quantum state and it evolves in time. And all these new rules have to do with what happens when you look at the system, when you observe it, when you measure it. In classical mechanics, there were no rules about observing. You just look at it and you see what's going on. That was it, right? In quantum mechanics, the way we teach it, there's something profoundly fundamental about the act of measurement or observation, and the system dramatically changes its state. Even though it has a wave function, like the electron in an atom is not orbiting in a circle, it's sort of spread out in a cloud. When you look at it, you don't see that cloud. When you look at it, it looks like a particle with a location. So it dramatically changes its state right away, and the effects of that change can be instantly seen in what the electron does next. So that's again, we need to be careful because we don't agree on what quantum mechanics says. So that's why I need to say, like, in the textbook view, et cetera, right? But in the textbook view, quantum mechanics, unlike any other theory of physics, gives a fundamental role to the act of measurement.
So maybe even more basic, what is an atom and what is an electron?
Sure. This all came together, in a few years around the turn of the last century, right? Around the year 1900. Atoms predated then. Of course, the word atom goes back to the ancient Greeks, but it was the chemists in the 1800s that really first got experimental evidence for atoms. They realized, that there were two different types of tin oxide. And in these two different types of tin oxide, there was exactly twice as much oxygen in one type as the other. And why is that? Why is it never 1.5 times as much, right? And so Dalton said, well, it's because there are tin atoms and oxygen atoms, and one form of tin oxide is one atom of tin and one atom of oxygen, and the other is one atom of tin and two atoms of oxygen. Mm-hmm. And on the basis of this, so this is a speculation, a theory, right, a hypothesis. But then on the basis of that, you make other predictions, and the chemists became quickly convinced that atoms were real. Yeah. The physicists took a lot longer to catch on, but eventually they did. And I mean, Boltzmann, who believed in atoms, he had a really tough time his whole life because he worked in Germany where atoms were not popular. They were popular in England, but not in Germany.
And in general, the idea of atoms is it's the smallest building block of the universe for them. That's the kind of how they thought about it.
That was the Greek idea, but the chemists in the 1800s jumped the gun a little bit. So these days, an atom is the smallest building block of a chemical element, right? Hydrogen, tin, oxygen, carbon, whatever. But we know that atoms can be broken up further than that. And that's what physicists discovered in the early 1900s, Rutherford especially, and his colleagues. So the atom that we think about now, the cartoon, is that picture you've always seen of a little nucleus and then electrons orbiting it like a little solar system. And we now know the nucleus is made of protons and neutrons. So the weight of the atom, the mass, is almost all in its nucleus. Protons and neutrons are something like 1,800 times as heavy as electrons are. Electrons are much lighter, but because they're lighter, they give all the life to the atoms. So when atoms get together, combine chemically, when electricity flows through a system, it's all the electrons that are doing all the work.
And where quantum mechanics steps in, as you mentioned, with the position of velocity, with classical mechanics, and quantum mechanics is modeling the behavior of the electron. I mean, you can model the behavior of anything, but the electron, because that's where the fun is.
The electron was the biggest challenge right from the start, yeah.
So what's a wave function? You said it's an interesting detail.
Yeah.
But in any interpretation, what is the wave function in quantum mechanics?
Well, we had this idea from Rutherford that atoms look like little solar systems. But people very quickly realized that can't possibly be right. Because if an electron is orbiting in a circle, it will give off light. All the light that we have in this room comes from electrons zooming up and down and wiggling, and that's what electromagnetic waves are. And you can calculate how long would it take for the electron just to spiral into the nucleus. And the answer is 10 to the minus 11 seconds, okay? 100 billionth of a second. So that's not right. Meanwhile, people had realized that light, which we understood from the 1800s was a wave, had properties that were similar to that of particles, right? This is Einstein and Planck and stuff like that. So if something that we agree was a wave had particle-like properties, then maybe something we think is a particle, the electron, has wave-like properties, right? And so a bunch of people eventually came to the conclusion, don't think about the electron as a little point particle orbiting in, like a solar system. Think of it as a wave that is spread out. And they cleverly gave this the name the wave function, which is the dopiest name in the world for one of the most profound things in the universe. There's literally, a number at every point in space, which is the value of the electron's wave function at that point.
And there's only one wave function.
They eventually figured that out. That took longer. Mm-hmm. But when you have two electrons, you do not have a wave function for electron 1 and a wave function for electron 2. You have one combined wave function for both of them. And indeed, as you say, there's only one wave function for the entire universe at once.
Yeah, and that's where this beautiful dance. Can you say what is entanglement? It seems one of the most fundamental ideas of quantum mechanics.
Well, let's temporarily buy into the textbook interpretation of quantum mechanics. And what that says is that this wave function, so it's very small outside the atom, very big in the atom. Basically, the wave function, you take it and you square it. You square the number. That gives you the probability of observing the system at that location. So if you say that for two electrons, there's only one wave function, and that wave function gives you the probability of observing both electrons at once doing something, okay? So maybe the electron can be here or here, here, or here, and the other electron can also be there, but we have a wave function set up where we don't know where either electron is going to be seen, but we know they'll both be seen in the same place, okay? So we don't know exactly what we're going to see for either electron, but there's entanglement between the two of them. There's a sort of conditional statement. If we see one in one location, then we know the other one's going to be doing a certain thing. So that's a feature of quantum mechanics that is nowhere to be found in classical mechanics. In classical mechanics, there's no way I can say, well, I don't know where either one of these particles is, but if I find out where this one is, then I know where the other one is. That just never happens. They're truly separate.
And in general, it feels like if you think of a wave function like as a dance floor, it seems like entanglement is strongest between things that are dancing together closest. So there's a closeness that's important
Well, that's another step. We have to be careful here because in principle, if you're talking about the entanglement of two electrons, for example, they can be totally entangled or totally unentangled no matter where they are in the universe. There's no relationship between the amount of entanglement and the distance between two electrons. But we now know that, the reality of our best way of understanding the world is through quantum fields, not through particles. So even the electron, not just gravity and electromagnetism, but even the electron and the quarks and so forth are really vibrations in quantum fields. So even empty space is full of vibrating quantum fields. And those quantum fields in empty space are entangled with each other in exactly the way you just said. If they're nearby, if you have like two vibrating quantum fields that are nearby, then they will be highly entangled. If they're far away, they will not be entangled.
So what do quantum fields in a vacuum look like? Empty space?
Just looks like empty space. It's as empty as it can be.
But there's still a field. It's just... Yeah. What does nothing
just like right here, this location in space, there's a gravitational field, which I can detect by dropping something, right? I don't see it, but there it is.
So we got a little bit of a idea of entanglement. Now, what is Hilbert space and Euclidean space?
Yeah, I think that people are very welcome to go through their lives not knowing what Hilbert space is. But if you want to dig into a little bit more into quantum mechanics, it becomes necessary. The English language was invented long before quantum mechanics or various forms of higher mathematics were invented. So we use the word space to mean different things. Of course, most of us think of space as this three-dimensional world in which we live, right? I mean, some of us just think of it as outer space. But space around us, it gives us the three-dimensional location of things and objects. But mathematicians use any generic, abstract collection of elements as a space, okay? A space of possibilities, momentum space, etc. So Hilbert space is the space of all possible quantum wave functions, either for the universe or for some specific system. And it could be an infinite dimensional space, or it could be just really, really large dimensional, but finite. We don't know because we don't know the final theory of everything. But this abstract Hilbert space is really, really, really big and has no immediate connection to the three-dimensional space in which we live.
What do dimensions in Hilbert space mean?
It's just a way of mathematically representing how much information is contained in the state of the system. How many numbers do you have to give me to specify what the thing is doing? So in classical mechanics, I give you the location of something by giving you three numbers, right? Up, down, left, x, y, z coordinates. But then I might want to give you its entire state, physical state, which means both its position and also its velocity. And the velocity also has three components. So its state lives in something called phase space, which is six-dimensional, 3 dimensions of position, 3 dimensions of velocity. And then if it also has an orientation in space, that's another 3 dimensions and so forth. So as you describe more and more information about the system, you have an abstract mathematical space that has more and more numbers that you need to give, and each one of those numbers corresponds to a dimension in that space.
So in terms of the amount of information, what is entropy? This mystical word that's overused in math and physics, but has a very specific meaning in this context.
Sadly, it has more than one very specific meaning. This is the reason why it's hard. Entropy means different things even to different physicists. But one way of thinking about it is a measure of how much we don't know about the state of a system, right? So if I have a bottle of water molecules and I know that, okay, there's a certain number of water molecules, I could weigh it, right, and figure out. I know the volume of it and I know the temperature and pressure and things like that. I certainly don't know the exact position and velocity of every water molecule, right? So there's a certain amount of information I know, a certain amount that I don't know that is part of the complete state of the system. And that's what the entropy characterizes, how much unknown information there is, the difference between what I do know about the system and its full exact microscopic state.
So when we try to describe a quantum mechanical system, is it infinite or finite but very large?
Yeah, we don't know. It depends on the system. It's easy to mathematically write down a system that would have a potentially infinite entropy, an infinite dimensional Hilbert space. So let's go back a little bit. we said that the Hilbert space was the space in which quantum wave functions lived for different systems that will be different sizes. They could be infinite or finite. So that's the number of numbers, the number of pieces of information you could potentially give me about the system. So the bigger Hilbert space is, the bigger the entropy of that system could be, depending on what I know about it. If I don't know anything about it, then it has a huge entropy, right? But only up to the size of its Hilbert space. So we don't know in the real physical world whether or not this region of space that contains that water bottle has potentially an infinite entropy or just a finite entropy. We have different arguments on different sides.
So if it's infinite, how do you think about infinity? Is this something you can, your cognitive abilities are able to process, or is it just a mathematical tool?
It's somewhere in between, right? I mean, we can say things about it. We can use mathematical tools to manipulate infinity very, very accurately. We can define what we mean. For any number n, there's a number bigger than it. So there's no biggest number, right? So there's something called the total number of all numbers. And it's infinite. But it is hard to wrap your brain around that. And I think that gives people pause because we talk about infinity as if it's a number, but it has plenty of properties that real numbers don't have. If you multiply infinity by 2, you get infinity again, right? It's a little bit different than what we're used to.
Okay, but are you comfortable with the idea that in thinking of what the real world actually is, that infinity could be part of that world? Sure. Are you comfortable that a world in some dimension, in some aspect?
I'm comfortable with lots of things. I mean, I don't want my level of comfort to affect what I think about the world. I'm pretty open-minded about what the world could be at a fundamental level.
Yeah, but infinity is a tricky one. It's not almost a question of comfort. It's a question of is it an overreach of our intuition? Sort of, it could be a convenient, almost like when you add a constant to an equation just because it'll help. It just feels like it's useful to at least be able to imagine a concept, not directly, but in some kind of way that this feels like it's a description of the real world.
Think of it this way. There's only 3 numbers that are simple. There's 0, there's 1, and there's infinity. A number like 318 is just bizarre. Like that you need a lot of bits to give me what that number is.
Yeah.
But 0 and 1 and infinity, like once you have 300 things, you might as well have infinity things, right? Otherwise, you have to say when to stop making the things, right? So there's a sense in which infinity is a very natural number of things to exist.
I was never comfortable with infinity because it's just it was too good to be true. Because in math, it just helps make things work out. When things get very large, close to infinity, things seem to work out nicely. It's kind of like, because my deepest passion is probably psychology. Mm-hmm. And I'm uncomfortable how in the average, the beauty of how much we vary is lost. In that same kind of sense, infinity seems like a convenient way to erase the details.
But the thing about infinity is it seems to pop up whether we like it or not. Right? Like you're trying to be a computer scientist, you ask yourself, well, how long will it take this program to run? Right. And you realize, well, for some of them, the answer is infinitely long. Yeah. It's not because you tried to get there. You wrote a 5-line computer program. It doesn't halt.
So coming back to the textbook definition of quantum mechanics, this idea that I don't think we talked about, one of the most interesting philosophical points, we talked at the human level, but at the physics level, that at least the textbook definition of quantum mechanics separates what is observed and what is real. How does that make you feel? And 2, what does it then mean to observe something, and why is it different than what is real?
Yeah, my personal feeling, such as it is that things like measurement and observers and stuff like that are not going to play a fundamental role in the ultimate laws of physics. But my feeling that way is because so far that's where all the evidence has been pointing. I could be wrong, and there's certainly a sense in which it would be infinitely cool if somehow observation or mental cogitation did play a fundamental role in the nature of reality. But I don't think so. And again, I don't see any evidence for it. So I'm not spending a lot of time worrying about that possibility. So what do you do about the fact that in the textbook interpretation of quantum mechanics, this idea of measurement or looking at things seems to play an important role? Well, you come up with better interpretations of quantum mechanics, and there are several alternatives. My favorite is the many worlds interpretation, which says two things. Number one, you, the observer, are just a quantum system like anything else. There's nothing special about you. Don't get so proud of yourself. You're just a bunch of atoms. You have a wave function. You obey the Schrodinger equation like everything else. And number two, when you think you're measuring something or observing something, what's really happening is you're becoming entangled with that thing. So when you think that there's a wave function for the electron, it's all spread out, but you look at it and you only see it in one location. What's really happening is that there's still the wave function for the electron in all those locations, but now it's entangled with the wave function of you in the following way. There's part of the wave function that says the electron was here and you think you saw it there. The electron was there and you think you saw it there. The electron was over there and you think you saw it there, etc. So, and all of those different parts of the wave function, once they come into being, no longer talk to each other. They no longer interact or influence each other. It's as if they are separate worlds. So this was the invention of Hugh Everett III, who was a graduate student at Princeton in the 1950s. And he said, basically, look, you don't need all these extra rules about looking at things. Just listen to what the Schrodinger equation is telling you. It's telling you that you have a wave function, that you become entangled, and that the different versions of you no longer talk to each other. So just accept it. It's just, he did therapy more than anything else. He said, like, it's okay. You don't need all these extra rules. All you need to do is believe the Schrodinger equation. The cost is there's a whole bunch of extra worlds out there.
So the world's being created, whether there's an observer or not.
The worlds are created anytime a quantum system that's in a superposition becomes entangled with the outside world.
What's the outside world?
It depends. Let's back up.
Yep.
Whatever it really says, what his theory is there's a wave function of the universe and it obeys the Schrodinger equation all the time. That's it. That's the full theory right there, okay? The question, all of the work, is how in the world do you map that theory onto reality, onto what we observe, right? So part of it is carving up the wave function into these separate worlds, saying, look, it describes a whole bunch of things that don't interact with each other. Let's call them separate worlds. Another part is distinguishing between systems and their environments. And the environment is basically all the degrees of freedom, all the things going on in the world that you don't keep track of. So again, in the bottle of water, I might keep track of the total amount of water and the volume. I don't keep track of the individual positions and velocities. I don't keep track of all the photons or the air molecules in this room. So that's the outside world. The outside world is all the parts of the universe that you're not keeping track of when you're asking about the behavior of subsystem of it.
So how many worlds are there?
Yeah, we don't know that one either. There could be an infinite number. There could be only a finite number, but it's a big number one way or the other.
So it's a very, very big number. In one of the talks, somebody asked, well, if it's finite. So actually, I'm not sure exactly the logic you used to derive this, but is there, going to be, overlap, a duplicate world that you return to? So you've mentioned, and I'd love if you can elaborate on sort of idea that it's possible that there's some kind of equilibrium that these splitting worlds arrive at, and then maybe over time, maybe somehow connected to entropy, you get a large number of worlds that are very similar to each other.
Yeah, so this question of whether or not Hilbert space is finite or infinite dimensional is actually secretly connected to gravity and cosmology. This is the part that we're still struggling to understand right now. But we discovered back in 1998 that our universe is accelerating. And what that means, if it continues, which we think it probably will, but we're not sure. But if it does, that means there's a horizon around us. Because the universe is not only expanding, but expanding faster and faster, things can get so far away from us that from our perspective, it looks like they're moving away faster than the speed of light. We will never see them again. So there's literally a horizon around us, and that horizon approaches some fixed distance away from us. And you can then argue that within that horizon, there's only a finite number of things that can possibly happen, the finite dimensional Hilbert space. In fact, we even have a guess for what the dimensionality is. It's 10 to the power of 10 to the power of 122. That's a very large number.
Yes.
Just to compare, the age of the universe is something like 10 to the 14 seconds, 10 to the 17 or 18 seconds maybe. The number of particles in the universe is 10 to the 88th. But the number of dimensions of Hilbert space is 10 to the 10 to the 122. So that's just crazy big. If that story is right, that in our observable horizon, there's only a finite dimensional Hilbert space, then this idea of branching of the wave function of the universe into multiple distinct separate branches has to reach a limit at some time. Once you branch that many times, you run out of room in Hilbert space. And roughly speaking, that corresponds to the universe just expanding and emptying out and cooling off and entering a phase where it's just empty space literally forever.
What's the difference between splitting and copying, do you think? Like in terms of, a lot of this is an interpretation that helps us sort of model the world. So perhaps shouldn't be thought of as like, philosophically or metaphysically, but even at the physics level, do you see a difference between sort of generating new copies of the world or splitting?
I think it's better to think of, in quantum mechanics, in many worlds, the universe splits rather than new copies, because people otherwise worry about things like energy conservation. Right. And no one who understands quantum mechanics worries about energy conservation because the equation is perfectly clear. But if all you know is that someone told you the universe duplicates, then you have a reasonable worry about where all the energy for that came from. So a pre-existing universe splitting into two skinnier universes is a better way of thinking about it. And mathematically, it's just like, if you draw an x and y axis and you draw a vector of length 1 at 45-degree angle, you know that you can write that vector of length 1 as the sum of two vectors pointing along x and y of length 1 over the square root of 2. Okay? So I write one arrow as the sum of two arrows. But there's a conservation of arrowness, right? Like there's now two arrows, but the length is the same. I'm describing it in a different way. And that's exactly what happens when the universe branches. The wave function of the universe is a big old vector.
So to somebody who brings up a question of saying, doesn't this violate the conservation of energy? Can you give a further elaboration?
Right. So let's just be super duper perfectly clear.
Yeah.
There's zero question about whether or not many worlds violates conservation of energy.
Yes.
It does not.
Great.
And I say this definitively because there are other questions that I think there's answers to, but they're legitimate questions, right? About, where does probability come from and things like that. This conservation of energy question, we know the answer to it, and the answer to it is that energy is conserved.
Yes.
All of the effort goes into how best to translate what the equation unambiguously says into plain English, right?
Right.
So this idea that there's a universe that has that the universe comes equipped with a thickness and it sort of divides up into thinner pieces, but the total amount of universe is conserved over time is a reasonably good way of putting English words to the underlying mathematics.
So one of my favorite things about many worlds is, I love that there's something controversial in science, and for some reason it makes people actually not like upset, but just get excited. Why do you think it is a controversial idea? So there's a lot of, it's actually one of the cleanest ways to think about quantum mechanics.
Yeah.
So why do you think there's a discomfort a little bit amongst certain people?
Well, I draw the distinction in my book between two different kinds of simplicity in a physical theory. There's simplicity in the theory itself, right? How we describe what's going on according to the theory by its own rights. But then, a theory is just some sort of abstract mathematical formalism. You have to map it onto the world somehow, right? And sometimes, like for Newtonian physics, it's pretty obvious. Like, okay, here is a bottle and it has a center of mass and things like that. Sometimes it's a little bit harder. With general relativity, curvature of space-time is a little bit harder to grasp. Quantum mechanics is very hard to map the language you're talking in of wave functions and things like that onto reality. And many worlds is the version of quantum mechanics where it is hardest to map on the underlying formalism to reality. So that's where the lack of simplicity comes in, not in the theory, but in how we use the theory to map onto reality. And in fact, all of the work in sort of elaborating many worlds quantum mechanics is in this effort to map it on to the world that we see. So it's perfectly legitimate to be bugged by that, right? To say like, well, no, that's just too far away from my experience. I am therefore intrinsically skeptical of it. Of course, you should give up on that skepticism if there are no alternatives and this theory always keeps working, then eventually you should overcome your skepticism. But right now there are alternatives that people work to make alternatives that are by their nature closer to what we observe directly.
Can you describe the alternatives? I don't think we touched on it. Sort of the Copenhagen interpretation and the many worlds. Maybe there's a difference between the Everettian many worlds and many worlds as it is now. Like has the idea sort of developed and so on. And just in general, what is the space of promising contenders? We have democratic debates now. There's a bunch of candidates.
12 candidates
12 candidates on stage. What are the quantum mechanical candidates on stage for the debate?
So if you had a debate between quantum mechanical contenders, there would be no problem getting 12 people up there on stage, but there would still be only 3 frontrunners. Yes. And right now the frontrunners would be Everett. Hidden variable theories are another one. So the hidden variable theories say that the wave function is real, but there's something in addition to the wave function. The wave function is not everything. It's part of reality, but it's not everything. What else is there? We're not sure. But in the simplest version of the theory, they're literally particles. So many worlds says that quantum systems are wave-like in some ways and particle-like in another because they really, really are waves, but under certain observational circumstances, they look like particles. Whereas hidden variable says they look like waves and particles because there are both waves and particles involved in the dynamics. And that's easy to do if your particles are just non-relativistic Newtonian particles moving around. They get pushed around by the wave function, roughly. It becomes much harder when you take quantum field theory or quantum gravity into account. The other big contender are spontaneous collapse theories. So in the conventional textbook interpretation, we say when you look at a quantum system, its wave function collapses and you see it in one location. A spontaneous collapse theory says that every particle has a chance per second of having its wave function spontaneously collapse. The chance is very small. For a typical particle, it will take hundreds of millions of years before it happens even once. But in a table or some macroscopic object, there are way more than 100 million particles, and they're all entangled with each other. So when one of them collapses, it brings everything else along with it. There's a slight variation of this. That's a spontaneous collapse theory. There are also induced collapse theories, like Roger Penrose thinks that when the gravitational difference between two parts of the wave function becomes too large, the wave function collapses automatically. So those are basically, in my mind, the 3 big alternatives. Many worlds, which is just there's a wave function, it always obeys the Schrodinger equation. Hidden variables, there's a wave function that always obeys the Schrodinger equation, but there are also new variables. Or collapse theories, which the wave function sometimes obeys the Schrodinger equation and sometimes it collapses. So you can see that the alternatives are more complicated in their formalism than many worlds is, but they are closer to our experience.
So just this moment of collapse, do you think of it as, so is a wave function fundamentally sort of a probabilistic description of the world? And is collapse sort of reducing that part of the world into something deterministic, where again you can now describe the position and the velocity in this simple classical model?
Well,
is that how you think about collapse?
There is a 4th category, there's a 4th contender. There's a Mayor Pete of quantum mechanical interpretations, which are called epistemic interpretations. And what they say is all the wave function is a way of making predictions for experimental outcomes. It's not mapping onto an element of reality in any real sense. And in fact, 2 different people might have 2 different wave functions for the same physical system because they know different things about it, right? The wave function is really just a prediction mechanism. And then the problem with those epistemic interpretations is if you say, okay, but it's predicting about what? Like, what is the thing that is being predicted? And they say, no. That's not what we're here for. We're just here to tell you what the observational outcomes are going to be.
But the other interpretations kind of think that the wave function is real.
Yes, that's right. So that's an ontic interpretation of the wave function, ontology being the study of what is real, what exists, as opposed to an epistemic interpretation of the wave function, epistemology being the study of what we know.
I would actually just love to see that debate on stage.
There was a version of it on stage at the World Science Festival a few years ago that you can look up online.
And on YouTube?
Yep, it's on YouTube.
Okay, awesome. I'll link it and watch it.
Many worlds.
Who won?
I won. No, I don't know. There was no vote. There was no vote. But there's Brian Greene was the moderator, and David Albert stood up for spontaneous collapse, and Shelley Goldstein was there for hidden variables, and Rudiger Schock was there for epistemic approaches.
Why do you? I think you mentioned it, but just to elaborate, why do you find many worlds so compelling?
Well, there's two reasons, actually. One is, like I said, it is the simplest, right? It's like the most bare bones, austere, pure version of quantum mechanics. And I am someone who is very willing to put a lot of work into mapping the formalism onto reality. I'm less willing to complicate the formalism itself. But the other big reason is that there's something called modern physics with quantum fields and quantum gravity and holography and spacetime, doing things like that. And when you take any of the other versions of quantum theory, they bring along classical baggage. All of the other versions of quantum mechanics prejudice or privilege some version of classical reality, like locations in space, okay? And I think that that's a barrier to doing better at understanding the theory of everything and understanding quantum gravity and the emergence of space-time. Whenever, if you change your theory from, here's a harmonic oscillator, there's a spin, here's an electromagnetic field, in hidden variable theories or dynamical collapse theories, you have to start from scratch. You have to say, like, well, what are the hidden variables for this theory, or how does it collapse, or whatever. Whereas many worlds is plug and play. You tell me the theory and I can give you its many worlds version. So when we have a situation like we have with gravity and space-time, where the classical description seems to break down in a dramatic way, then I think you should start from the most quantum theory that you have, which is really many worlds.
So start with the quantum theory and try to build up a model of space-time, the emergence of space-time.
That's right.
Okay, so I thought space-time was fundamental.
Yeah, I know.
So this sort of dream that Einstein had, that everybody had and everybody has, of, the theory of everything. So how do we build up from many worlds, from quantum mechanics, a model of space-time, model of gravity?
Well, yeah, let me first mention very quickly why we think it's necessary. We've had gravity in the form that Einstein bequeathed it to us for over 100 years now. Like 1915 or 1916, he put general relativity in the final form. So gravity is the curvature of space-time, and there's a field that pervades all the universe that tells us how curved space-time is.
And that's a fundamentally classical...
That's totally classical, right? Exactly. But we also have a formalism, an algorithm for taking a classical theory and quantizing it. This is how we get quantum electrodynamics, for example. And it could be tricky. You think you're quantizing something. So that means taking a classical theory and promoting it to a quantum mechanical theory. But you can run into problems. So they ran into problems when they did that with electromagnetism, namely that certain quantities were infinity, and you don't like infinity, right?
Nope.
So Feynman and Tominaga and Schwinger won the Nobel Prize for teaching us how to deal with the infinities. And then Ken Wilson won another Nobel Prize for saying you shouldn't have been worried about those infinities after all. But still, it's always the thought that that's how you will make a good quantum theory. You'll start with a classical theory and quantize it. So if we have a classical theory, general relativity, we can quantize it, or we can try to, but we run into even bigger problems with gravity than we ran into with electromagnetism. And so far, those problems are insurmountable. We've not been able to get a successful theory of gravity, quantum gravity, by starting with classical general relativity and quantizing it. And there's evidence that there's a good reason why this is true, that whatever the quantum theory of gravity is, it's not a field theory. It's something that has weird non-local features built into it somehow that we don't understand. And we get this idea from black holes and Hawking radiation and information conservation and a whole bunch of other ideas I talk about in the book. So if that's true, if the fundamental theory isn't even local in the sense that an ordinary quantum field theory would be, then we just don't know where to start in terms of getting a classical precursor and quantizing it.
Right.
So the only sensible thing, at least the next obvious sensible thing to me would be to say, okay, let's just start intrinsically quantum and work backwards, see if we can find a classical limit.
So the idea of locality, the fact that locality is not fundamental to the nature of our existence, sort of, I guess in that sense, modeling everything as a field makes sense to me. Stuff that's close by interacts, stuff that's far away doesn't. So what's locality and why is it not fundamental? And how is that even possible?
Yeah, I mean, locality is the answer to the question that Isaac Newton was worried about back at the beginning of our conversation, right? I mean, how can the Earth know what the gravitational field of the sun is? And the answer, as spelled out by Laplace and Einstein and others, is that there's a field in between. And the way a field works is that what's happening to the field at this point in space only depends directly on what's happening at points right next to it. But what's happening at those points depends on what's happening right next to those, right? And so you can build up an influence across space through only local interactions. That's what locality means. What happens here is only affected by what's happening right next to it. That's locality. The idea of locality is built into every field theory, including general relativity as a classical theory. It seems to break down when we talk about black holes. And, Hawking taught us in the 1970s that black holes radiate. They give off, they will eventually evaporate away. They're not completely black once we take quantum mechanics into account. And we don't know for sure, but most of us think that if you make a black hole out of certain stuff, then like Laplace's demon taught us, you should be able to predict what that black hole will turn into, if it's just obeying the Schrodinger equation. And if that's true, there are good arguments that can't happen while preserving locality at the same time. It's just that the information seems to be spread out non-locally in interesting ways.
And people should, you talk about holography with Leonard Susskind on your Mindscape podcast. People should
yes, I have a podcast. I didn't even mention that. I'm terrible at
No, I'm gonna ask you questions about that too. And I've been not shutting up about it. It's my favorite science podcast. So, or not, it's not even a science podcast. It's like it's a scientist doing a podcast.
That's right. That's what it is. Absolutely. Yes.
Yeah. Okay. Anyway.
So holography is this idea when you have a black hole, and black hole is a region of space inside of which gravity is so strong that you can't escape. And there's this weird feature of black holes that, again, is totally a thought experiment feature because we haven't gone and probed any yet. But there seems to be one way of thinking about what happens inside a black hole as seen by an observer who's falling in, which is actually pretty normal. Like everything looks pretty normal until you hit the singularity and you die. But from the point of view of the outside observer, it seems like all the information that fell in is actually smeared over the horizon in a non-local way. And that's puzzling. And that's so holography, because that's a two-dimensional surface that is encapsulating the whole three-dimensional thing inside, right? Still trying to deal with that, still trying to figure out how to get there. But it's an indication that we need to think a little bit more subtly when we quantize gravity.
So because you can describe everything that's going on in in three-dimensional space by looking at the two-dimensional projection of it, means that locality is not necessary.
Well, it means it's only a good approximation. It's not really what's going on.
How are we supposed to feel about that?
We're supposed to feel liberated. Space is just a good approximation. And this was always going to be true once you started quantizing gravity. So we're just beginning now to face up to the dramatic implications of quantizing gravity.
Is there other weird stuff that happens to quantum mechanics in a black hole?
I don't think that anything weird has happened with quantum mechanics. I think weird things happen with spacetime. I mean, that's what it is. Like quantum mechanics is still just quantum mechanics, but our ordinary notions of spacetime don't really quite work. And there's a principle that goes hand in hand with holography called complementarity, which says that there's no one unique way to describe what's going on inside a black hole. Different observers will have different descriptions, both of which are accurate, but sound completely incompatible with each other. So it depends on how you look at it. The word complementarity in this context is borrowed from Niels Bohr, who points out you can measure the position or you can measure the momentum. You can't measure both at the same time in quantum mechanics.
So a couple of questions on many worlds. How does many worlds help us understand our particular branch of reality? So, okay, that's fine and good that everything is splitting, but we're just traveling down a single branch of it. So how does it help us understand our little unique branch?
Yeah, I mean, that's a great question, but that's the point, is that we didn't invent many worlds because we thought it was cool to have a whole bunch of worlds, right? We invented it because we were trying to account for what we observe here in our world.
Yeah.
And what we observe here in our world are wave functions collapsing. Okay, we do have a situation where the electron seems to be spread out, but then when we look at it, we don't see it spread out. We see it located somewhere. So what's going on? That's the measurement problem of quantum mechanics. That's what we have to face up to. So many worlds is just a proposed solution to that problem. And the answer is nothing special is happening. It's still just the Schrodinger equation, but you have a wave function too. And that's a different answer than would be given in hidden variables or dynamical collapse theories or whatever. So the entire point of many worlds is to explain what we observe, but it tries to explain what we already have observed, right? It's not trying to be different from what we've observed, because that would be something other than quantum mechanics.
But, the idea that there's worlds that we didn't observe that keep branching off is kind of, it's stimulating to the imagination. So is it possible to hop from, you mentioned the branches are independent.
Yeah.
So, is it possible to hop from one to the other?
No.
It's a physical limit.
Yeah.
The theory says it's impossible.
There's already a copy of you in the other world. Don't worry.
Yes.
Then leave them alone.
No, but there's a fear of missing out, FOMO.
Yes.
That I feel like I immediately start to wonder if that other copy is having more or less fun.
Yeah, well, the downside of many worlds is that you're missing out on an enormous amount. and that's always what it's going to be like.
And there's a certain stage of acceptance in that.
Yes.
In terms of rewinding, do you think we can rewind the system back? Sort of the nice thing about many worlds, I guess, is it really emphasizes maybe you can correct me, but the deterministic nature of a branch. And it feels like it could be rewound back. Do you see it as something that could be perfectly rewinded back? Yeah.
If you're at a fancy French restaurant,
yes,
and there's a nice linen white tablecloth, and you have your glass of Bordeaux, and you knock it over, and the wine spills across the tablecloth. If the world were classical, okay, it would be possible that if you just lifted the wine glass up, you'd be lucky enough that every molecule of wine would hop back into the glass, yep, right? But guess what? It's not going to happen in the real world. And the quantum wave function is exactly the same way. It is possible in principle to rewind everything if you start from perfect knowledge of the entire wave function of the universe. Mm-hmm. In practice, that's never going to happen.
So time travel, not possible.
Nope. At least quantum mechanics has no help.
What about memory? Does the universe have a memory of itself where we could, so not time travel, but peek back in time and do a little like replay?
Well, it's exactly the same in quantum mechanics as classical mechanics. So whatever you want to say about that, the fundamental laws of physics in either many worlds quantum mechanics or Newtonian physics conserve information. So if you have all the information about the quantum state of the world right now, your Laplace's demon-like in your knowledge and calculational capacity, you can wind the clock backward. But none of us is, right? And, so in practice, you can never do that. You can do experiments over and over again, starting from the same initial conditions for small systems. But once things get to be large, Avogadro's number of particles, right? Bigger than a cell, no chance.
We talked a little bit about arrow of time last time, but in many worlds that there is a kind of implied arrow of time, right? So you've talked about the arrow of time that has to do with the second law of thermodynamics. That's the arrow of time that's emergent or fundamental. We don't know, I guess.
No, it's emergent.
Does everyone agree on that? Well, nobody
They
agrees with
should.
everything.
They should.
They should. So that arrow of time, is that different than the arrow of time that's implied by many worlds?
It's not different, actually. No. In both cases, you have fundamental laws of physics that are completely reversible. If you give me the state of the universe at one moment in time, I can run the clock forward or backward equally well. There's no arrow of time built into the laws of physics at the most fundamental level. But what we do have are special initial conditions 14 billion years ago near the Big Bang. In thermodynamics, those special initial conditions take the form of things were low entropy, and entropy has been increasing ever since, making the universe more disorganized and chaotic, and that's the arrow of time. In quantum mechanics, these special initial conditions take the form of there was only one branch of the wave function, and the universe has been branching more and more ever since.
Okay, so if time is emergent, so it seems like our human cognitive capacity likes to take things that are emergent and assume and feel like they're fundamental. So if time is emergent and locality, like is space emergent?
Yes.
Okay.
But I didn't say time was emergent. I said the arrow of time was emergent. Those are different.
What's the difference between the arrow of time and time? Are you using arrow of time to simply mean this? They're synonymous with the second law of thermodynamics?
No, but the arrow of time is the difference between the past and future. So There's space, but there's no arrow of space. You don't feel that space has to have an arrow, right? You could live in thermodynamic equilibrium. There'd be no arrow of time, but there'd still be time. There'd still be a difference between now and the future or whatever.
Okay. So if nothing changes, there's still time.
Well, things could even change. Like if the whole universe consisted of the Earth going around the sun, okay, it would just go in circles or ellipses, right?
That's an equilibrium.
Things would change, but it's not increasing entropy. There's no arrow. If you took a movie of that and I played you the movie backward, you would never know.
So the arrow of time can theoretically point in the other direction for briefly.
To the extent that it points in different directions, it's not a very good arrow. I mean, the arrow of time in the macroscopic world is so powerful that there's just no chance of going back. When you get down to tiny systems with only 3 or 4 moving parts, then entropy can fluctuate up and down.
What does it mean for space to be an emergent phenomenon?
It means that the fundamental description of the world does not include the word space. It'll be something like a vector in Hilbert space, right? And you have to say, well, why is there a good approximate description which involves 3-dimensional space and stuff inside it?
Okay, so time and space are emergent. We kind of mentioned it in the beginning, but can you elaborate? What do you hope is fundamental in our universe?
A wave function living in Hilbert space.
A wave function in Hilbert space that we can't intellectualize or visualize, really.
We can't visualize it. We can intellectualize it very easily.
Like, well, how do you think about...
It's a vector in a 10 to the 10 to the 122 dimensional vector space. It's a complex vector, unit norm. It evolves according to the Schrodinger equation.
Got it. When you put it that way.
What's so hard, really?
It's like, yep. Quantum computers. There's some excitement, actually a lot of excitement with people that it will allow us to simulate quantum mechanical systems. What kind of questions about quantum mechanics, about the things we've been talking about, do you hope we can answer through quantum simulation?
Well, I think that there's a whole fascinating frontier of things you can do with quantum computers, both sort of practical things with cryptography or money, privacy eavesdropping, sorting things, simulating quantum systems, right?
So it's a broader question, maybe even outside of quantum computers. Some of the theories that we've been talking about, what's your hope? What's most promising to test these theories? What are kind of experiments we can conduct, whether in simulation or in the physical world, that would validate or disprove or expand these theories?
Well, I think there's 2 parts of that question. One is many worlds, and the other one is sort of emergent space time. For many worlds, there are experiments ongoing to test whether or not wave functions spontaneously collapse. And if they do, then that rules out many worlds, and that would be falsified. if there are hidden variables, there's a theorem that seems to indicate that the predictions will always be the same as many worlds. I'm a little skeptical of this theorem. I haven't internalized it. I haven't made it in part of my intuitive view of the world yet. So there might be loopholes to that theorem. I'm not sure about that. Part of me thinks that there should be different experimental predictions if there are hidden variables, but I'm not sure. But otherwise, it's just quantum mechanics all the way down. And so there's this cottage industry in science journalism of writing breathless articles that say, quantum mechanics shown to be more astonishing than ever before thought. And really, it's the same quantum mechanics we've been doing since 1926. Whereas with the emergent spacetime stuff, we know a lot less about what the theory is. It's in a very primitive state. We don't even really have a safely written down, respectable, honest theory yet. So there could very well be experimental predictions we just don't know about yet. That is one of the things that we're trying to figure out.
But for emergent space-time, you need really big stuff, right?
Well, or really fast stuff, or really energetic stuff. We don't know. That's the thing. So there could be violations of the speed of light if you have emergent space-time. Not going faster than the speed of light, but the speed of light could be different for light of different wavelengths, right? That would be a dramatic violation of physics as we know it, but it could be possible. Or not. I mean, it's not an absolute prediction. That's the problem. The theories are just not well developed enough yet to say.
Is there anything that quantum mechanics can teach us about human nature or the human mind? Do you think about sort of consciousness and these kinds of topics? It's certainly excessively used, as you point out. The word quantum is used for everything besides quantum mechanics. But in more seriousness, is there something that goes to the human level and can help us understand our mind?
Not really is the short answer. Minds are pretty classical. I don't think, we don't know this for sure, but I don't think that phenomena like entanglement are crucial to how the human mind works.
What about consciousness? So you mentioned, I think early on in the conversation, you said it would be unlikely but incredible if sort of the observer is somehow a fundamental part. So if observer, not to romanticize the notion, but seems interlinked to the idea of consciousness. So if consciousness is, as the panpsychists believe, is fundamental to the universe, is that possible? Is that
everything's possible.
Just like Joe Rogan likes to say, it's entirely possible.
Right.
But is it on a spectrum of crazy out there? How like statistically speaking, how often do you ponder the possibility that consciousness is fundamental or the observer is fundamental to?
I personally don't at all. There are people who do. I'm a thorough physicalist when it comes to consciousness. I do not think that there are any separate mental states or mental properties. I think they're all emergent, just like space-time is. And, space-time is hard enough to understand. So the fact that we don't yet understand consciousness is not at all surprising to me.
You, as we mentioned, have an amazing podcast called Mindscape. It's, as I said, one of my favorite podcasts, sort of both for your explanation of physics, which a lot of people love, and when you venture out into things that are beyond your expertise. But it's just a really smart person exploring even questions like, morality, for example. It was very interesting. I think you did a solo episode and so on. I mean, there's a lot of really interesting conversations that you have. What are some, from memory, amazing conversations that pop to mind that you've had? What did you learn from them? Something that maybe changed your mind or just inspired you, or just what through this whole experience of having conversations, what stands out to you? It's an unfair question.
It's totally unfair, but that's okay. That's all right. It's often the ones, I feel like the ones I do on physics and closely related science, or even philosophy ones, are like, I know this stuff and I'm helping people learn about it. But I learn more from the ones that have nothing to do with physics or philosophy, right? So talking to Wynton Marsalis about jazz, or talking to a master sommelier about wine, talking to Will Wilkinson about partisan polarization and the urban-rural divide, talking to psychologists like Carroll Tavris, about cognitive dissonance and how those things work. Scott Derrickson, who is the director of the movie Doctor Strange, I had a wonderful conversation with him where we went through the mechanics of making a blockbuster superhero movie, right? And he's also not a naturalist; he's a evangelical Christian, so we talked about the nature of reality there. I want to have a couple more, discussions with highly educated theists who know the theology really well, but I haven't quite arranged those yet.
I would love to hear that. I mean, that's how comfortable are you venturing into questions of religion?
Oh, I'm totally comfortable doing it. I did talk with Alan Lightman, who is also an atheist, but he is trying to rescue the sort of spiritual side of things for atheism. And I did talk to very vocal atheists like Alex Rosenberg. So I need to talk to some. I've talked to some religious believers, but I need to talk to more.
How have you changed through having all these conversations?
Part of the motivation was I had a long stack of books that I hadn't read, and I couldn't find time to read them. And I figured if I interviewed their authors, it would force me to read them, right? Yeah. And that has totally worked, by the way. Now I'm annoyed that people write such long books. I think I'm still very much learning how to be a good interviewer. I think that's a skill that, I think I have good questions, but, there's the give and take that is still, I think I can be better at. Like, I want to offer something to the conversation, but not too much, right? I've had conversations where I barely talked at all, and I had conversations where I talked half the time, and I think there's a happy medium in between there.
So I think I remember listening to, without mentioning names, some of your conversations where I wish you would have disagreed more.
Yeah.
As a listener, it's more fun sometimes.
Well, that's a very good question because, everyone has an attitude toward that. Like some people are really there to basically give their point of view and their guest is supposed to, respond accordingly. I want to sort of get my view on the record, but I don't want to dwell on it when I'm talking to someone like David Chalmers, who I disagree with a lot. I want to say, like, here's why I disagree with you, but we're here to listen to you. Like, I have an episode every week, and you're only on once a week, right? Yeah. So I have an upcoming podcast episode with Philip Goff, who is a much more dedicated panpsychist. And so there we really get into it. I think that I probably have disagreed with him more on that episode than I ever have with another podcast guest. But that's what he wanted. So it worked very well.
Yeah. That kind of debate structure is beautiful when it's done right. Like when you can detect that the intent is that you have fundamental respect for the person.
Yeah.
And that's, for some reason, it's super fun to listen to when two really smart people are just arguing and sometimes lose their shit a little bit, if I may say so.
Well, there's a fine line because I have zero interest in bringing. Maybe you implied this. I have zero interest in bringing on people for whom I don't have any intellectual respect. Like I constantly get requests, like, bring on a flat earther or whatever and really slap them down, or a creationist. Like, I have zero interest. Yeah. I'm happy to bring on, a religious person, a believer, but I want someone who's smart and can act in good faith and can talk, not a charlatan or a lunatic, right? So I will happily bring on people with whom I disagree, but only people from whom I think the audience can learn something interesting.
So let me ask, the idea of charlatan is an interesting idea. You might be more educated on this topic than me, but there's folks, for example, who argue various aspects of evolution, sort of try to approach and say that evolution, sort of our current theory of evolution, has many holes in it, has many flaws. And they argue that, I think, like Cambrian explosion, which is like a huge added variability of species, doesn't make sense under our current description of evolution, the theory of evolution. Sort of, if you were to have the conversation with people like that, how do you know that the difference between outside the box thinkers and people who are fundamentally unscientific and even bordering on charlatans?
It's a great question. And, the further you get away from my expertise, the harder it is for me to really judge exactly those things. And I don't have a satisfying answer for that one, because I think the example you use of someone who, believes in the basic structure of natural selection, but thinks that, this particular thing cannot be understood in the terms of our current understanding of Darwinism, that's a perfect edge case where it's hard to tell, right? And I would try to talk to people who I do respect and who do know things, and I would have to, given that I'm a physicist, I know that physicists will sometimes be too dismissive of alternative points of view. I have to take into account that biologists can also be too dismissive of alternative points of view. So, it's a tricky one. And,
have you gotten heat yet?
I get heat all the time. Like, there's always something. I mean, it's hilarious because I try very hard not to have the same topic several times in a row. I did have 2 climate change episodes, but they were from very different perspectives. But I like to mix it up. That's why I'm having fun. And every time I do an episode, someone says, "Oh, the person you should really get on to talk about exactly that is this other person." I'm like, "Well, but I did that now. I don't want to do that anymore."
Well, I hope you keep doing it. You're inspiring millions of people with your books, with your podcast. Sean, it's an honor to talk to you. Thank you so much.
Thanks very much, Lex.